Hey guys, so in this video we're going to be talking about electricity and gravity. And actually we're going to talk about gravity first. So this is called Newton's law of universal gravitation, and it states this. It says the force of gravity, Fg, which this is just going to be the magnitude, is equal to this constant g, which we'll talk about in a second. It's capital G. Let me rewrite that. Um, so it's capital G times, now we've got, uh, I'm going to be writing it as a capital M and a lowercase m, but neither, they can be the same. That it's just, we're going to say that capital M, which is usually the bigger mass when we're talking about this, is going to be exerting a gravitational force on on the little m, right? So, and it actually turns out, based on Newton's third law, that actually if the one mass is exerting a gravitational force on the other is exerting a force on the the other one is exerting the same gravitational force on that mass back, right? So you're actually exerting the same gravitational force on the Earth as the Earth is exerting on you. But really, we just sort of want to talk about the force generally of the bigger mass on the smaller mass, but we can talk about it both ways. And hopefully you're familiar with this, so this is not too confusing, right? And so divided by the distance, the center to center distance between the masses squared, right? Which makes sense. The closer you are to a mass, which makes r smaller, which makes the force bigger. If, like the sun is a lot more massive than the Earth, this big M is a lot bigger for the sun. The sun has a stronger gravitational pull, not on Earth, because we're a lot closer to Earth, and this r squared term is going to be the one that dominates in terms of that. Okay, so now we know that force, though, is a vector, right? And so we can write this in a vector equation like this. So f of g vector hat is equal to g big M little m over r squared. Actually, we're going to throw a negative sign in front of it, and I'll explain that, times r hat. And r hat is a unit vector, right? R hat is the unit vector that points out, right? Out from the center of the planet, the bigger mass, of the mass causing the force that we're talking about. And the reason the negative sign is there is because the force of gravity is attractive. And so r hat points outwards, so the negative sign makes the force point inward. We also know that this is equal to the little mass times g. And it turns out g is, we call it the gravitational field, and sometimes it's called the gravitational acceleration. And the reason that is because if an object is in free fall, meaning the force of gravity is the only force on it, well, we know net force, right? Net force equals ma, right? Which, if we're talking about, right, the big M is exerting a force on little m, so this is Fg is equal to little m times a, right, which is mg is equal to ma, right? So we can cancel those out. If an object is in free fall, its acceleration is actually the gravitational field on it. And so the gravitational field, right? In fact, again, you exert a gravitational force on Earth. You have a gravitational field. It just happens the gravitational field is dependent on the capital M. Capital M is not necessarily bigger. It's just the mass causing the field, right? And since your mass is a lot smaller than the Earth's, your gravitational field is a lot less. But the force is actually the same, because the force, we're multiplying it by the Earth's mass, by the little m, if that's what we're talking about, right? But this is why usually, right, the acceleration is extremely small, because your gravitational field is really, really, really small. The other thing to note is, no matter what your mass is, right, the acceleration g only depends on the mass of the object causing it, right? So it's negative g over r squared, right, times r hat, right? It's not dependent on your mass or the mass of the object that the field is being applied to. It only depends on the mass of the object that is causing the field, right? Which is why everything on Earth accelerates at the same rate. So we can measure G, right? Force is measured in newtons, right? And we can measure G in the units of acceleration, meters per second squared, or we can also we can also measure it in we can measure it in newtons per kilogram, right? Which are equivalent units. So G is equal to about 6.67 times 10 to the negative 11th power. Now, if you want to figure out what the units are, well, this is in units of newtons, which is a kilogram times meter per second squared, or actually sorry, this is in newtons of kilograms times meters per second squared. I'm going to really focus on this equation actually, which is better. This is meters per second squared. Multiply by meters squared, so that would be meters cubed, divided by kilograms. So this would be meters cubed times seconds to the negative second times kilograms to the negative first. But notice that this is a really small number. To make, the little g, the gravitational field, significant at all, the mass has to be greater than, this number, or the distance has to be really, 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 really small. And so gravity is a really weak force, right? With a large mass, it can be strong, but on the quantum level, you need a really, really, really big mass to make gravity worth your while, and you're not going to get that on the quantum level. I mean, a proton has a mass of like, proton is heavy on the quantum scale, right? And has a mass of 10 to the it's around 10. It's on the order of magnitude of 10 to the negative 27th, I believe, kilograms. So that's, it's very small, right? Gravity does really not play a role in this. Okay, so now that we've talked about gravity, we'll talk about electricity. And electricity now, I'm going to erase this, hopefully you have it down. And if you don't understand anything here, go on Khan Academy. I've realized linking on Khan Academy, I really don't need to. You can just go to Khan Academy. It's linked in a bunch of my other videos. Just click on physics. It's very user-friendly. Click on physics. You can look at gravity. You can look at electricity. They'll explain this in more depth. Hopefully you're familiar with this. So this is pretty basic. So now we have the electric force, Fe, right? So the electric force, right, is we can do it with just the magnitude as well, but I'm just going to do it in the vector form. Okay, so we're going to have a capital Q, which is causing the field. And in general, really, capital Q isn't going to be bigger than lowercase q. I'm just calling it that to differentiate between the charges. Sometimes you'll see Q1, Q2, right? But here, capital Q is the charge causing the field. Lowercase q is the charge feeling the force, right? Or feeling the field. Both charges will feel an equal force, right? But like oftentimes, if we're dealing with a proton and an electron, the electron's force, because the proton is almost 2,000 times heavier than the electron, the proton is not going to really be accelerated. So the force isn't going to be that significant on the proton. The force on the electron will be significant. And so we'll be dealing, usually with one charge applying a significant force on the other charge, and or causing a significant acceleration, right? So that's why I'm gonna still do it like this. I'm hoping that made sense. So times r hat, right? And so a few things to notice. One, if capital Q and lowercase q have the same sign, right? This force is going to be positive in the r hat direction. The r hat direction is outward. It's a repulsive force, right? If they're negative signs, opposites attract, right? And if it's a negative sign, then it will be pointing inwards. The charges will be attracting, pulling inward to each other, just like gravity, right? So opposite signs will attract. Now this is equal to Q, right? The charge feeling the field, right? And again, both charges feel the field. It's just, usually we'll be talking one charge feels the field in a more significant way. So lowercase q, right, is the charge that we're putting in the field. Capital Q is the charge causing the field. And so it's QE. E is the electric field, E, right? And E is now, we'll see the sign will really matter. So KQ over R squared, right? Times R hat. So a positive charge has a field going outward, right? So a positive charge, the field will look like this. And it's going to be bigger when it's closer in, right? We can draw more. So this is sort of what the vector field just sort of shows, right? The longer lines means a larger magnitude of field, right? Same thing, right? And for a negative charge, it will be the opposite, right? It will pull in, right? This is what a gravitational field looks like. The field is and I don't need to draw the whole thing, but the field is the force on a positive charge, right? Because you can see if Q is negative, right, the force on a negative charge, that will actually flip the sign. So if E is in this direction, this is E. If the charge is positive, the force will also be in this direction. But if the charge is negative, Q will flip the sign, right? F equals QE. So the force will be in the opposite direction. So like the force on an electron is in the opposite direction of the electric field on that electron. Now, E is measured in newtons per coulomb, right? Because force is in newtons, right? And then, which is coulombs times the field of the electric field, right? Coulomb is the unit of charge, right? So the electric field, right, if you write E equals F over Q, right, you can see the units are newtons per coulomb. Now, what is K and what are the units of K? Well, the numerical value of K is about 9 times 10 to the 9th power, and its units. Well, let's see. We've got newtons per coulomb, right, times meters squared. So newtons times meters squared. And then here we have, we're dividing by another coulomb. So it's newtons times meters squared per coulomb squared, which would also be kilograms times meters cubed per second squared coulomb squared. If you just expand newtons as a kilogram times meters per second squared. So as you can see, this number is way bigger than capital G, right? The electric force is way, way, way stronger, right? This is 10 to the 9th. Capital G was to the order of magnitude 10 to the negative 11th, right? So that just shows that this one is a lot. The electric field is the electric force is a lot stronger than the gravitational force. That's why it will actually really matter on a quantum level, and we'll see that. The last thing I want to talk about is potential energy. So I'm gonna to use this tool. Yeah, I'm gonna erase this. And oftentimes, and especially in electricity, you'll see the capital V representing potential, not potential energy. And in quantum mechanics, this is just a convention that quantum mechanics textbooks use. I don't understand it. I don't really like it, but I'm going to use it because that is the standard convention in quantum mechanics. Potential energy is sometimes just called potential, and it's represented by a capital V, which is not what a capital V usually represents. Capital V usually represents potential, which is different than potential energy. But in quantum mechanics, we're calling it potential energy, or we're calling it potential, but it's actually potential energy. And if that confuses you, join the club. So for gravity, V sub g is the gravitational potential energy, negative g times the two masses, right, divided by r squared. This is a scalar, right? No vector. Sorry, not r squared. My bad. And I think I made that mistake in the other video too. It's not r squared. It's just r. And an electric potential energy is positive k, or not m, k times capital Q, lowercase q, right? K times both charges over r, right? And this defines potential energy equal to 0 at r equals infinity. Now, but if you remember from the video about energy, what really matters is the change in potential energy, right? And so if I were to graph this, right? You know, this is r. R can only be positive, right? It looks something like this, right? Same thing here. And this is for repulsion, right? If both charges are the same, this is for attraction here, right? You can see which direction, right? The force tries. Remember, the force tries to go, right? To get you to less potential energy, right? So if they're attractive, right, it tries to push you farther away, farther out. If it's if this is repulsive, it tries to push you farther out. If it's attractive, it tries to get you farther in, right? It wants you to have less potential energy. Hopefully you saw that in the other video. The important thing, right, is the force. It gives you kinetic energy, right? As you fall like towards the earth, right? You lose gravitational potential energy, right? But you gain kinetic energy. You start moving faster. And we talked about that the delta delta K, or really I'll call it delta T for kinetic energy, is equal to the negative delta U. So as you lose potential energy, you gain kinetic energy. And this is for conservative forces, which is what we're going to be dealing with in quantum mechanics. Oh, sorry, not U. And I'm so used to writing it as U. But in quantum mechanics, remember, we're going to be writing it as V, right? So this is our important equation. And kinetic energy, right, is 1/2 mv squared, which actually it's sometimes nicer to write p squared divided by 2m. P is momentum, so momentum squared divided by 2m, which is m squared v squared divided by 2m, which is mv squared divided by 2, right? But this is sometimes just an easier way, and we'll see in quantum mechanics this is a lot easier of a way to write this. And remember, this is a capital V as opposed to velocity, which is a lowercase v. So there's some very confusing conventions here, but hopefully this makes sense. And qualitatively, this makes sense, right? You lose potential energy. The force tries to get you to lose potential energy, and it does work on you. It makes you go faster, right? And the work the work done on you by a conservative force is equal to negative delta V. And we can show this also because the work kinetic energy theorem, right, which I think I talked about in the video on energy, is that the work done by a force is the change in kinetic energy, right? So hopefully this makes sense, especially this energy part. This is really important, that the change in kinetic energy is negative the change in potential energy, right? A force tries to get you to the lowest potential energy you can be at, and by doing that, it speeds you up. It does work on you. It moves you there. And you can think about, right, higher up, right? Higher up, it gets closer to 0 for gravitational potential energy. Lower down, this r is smaller. This number is bigger, but it's negative, right? Which is less, right? So it will look like this. It's going to be your potential energy graph. It tries to get you as close to the surface of the Earth as it can, right? down close to r equals 0. So you are accelerated this way, and as you go down, you gain potential energy, right? Or you gain kinetic energy, you lose potential energy, right? Which will make sense with this. Okay, so that is it. I'll see you in the next video.